Welcome again to the Theories of Everything program. I'm David Tao. Viewers, in our previous program we examined one of the two major outstanding puzzles confronting cosmologists today. That was the nature of dark matter. Now, dark matter, the unseen mass that surrounds galaxies and exists throughout the universe, is understood to exist because the current ordinary matter that we can see is just not sufficient to hold those galaxies together. And it also doesn't account for the nature, the spatially flat nature of the universe that's predicted by the inflationary model and has been since confirmed by the satellite probes examining the cosmic microwave background. Einstein's theory predicts that if the universe is spatially flat, then there has to be a critical density of mass and energy to maintain that shape. And at the moment, it appears from the latest theories that the amount of ordinary matter, baronic matter, half of which only is apparent, because half of it's hidden in the form of burnt-out stars, planets, and perhaps a lot of gas that's been drawn in from the outside space into the galactic centres and heated up. But that 4% is nowhere near enough to reach that critical density. And so the search has been on for dark matter, and there's a number of candidates, as we discussed in the previous program. The candidates, and the most promising candidates, include exotic sorts of particles that were created in the Big Bang, perhaps in other dimensions of the original universe, and they're still here today, and they feel the force of gravity and therefore clump in around the halos of the galaxies that we can see. And that appears, from the latest theories, the latest evidence, to account for around about 23% of the total mass energy required to keep the universe cosmologically consistent, if you like. So that's a total of 27%. So there's a missing amount of mass energy, around about a large chunk of it, in fact, around about 73%. So our discussion in this program will centre on the nature of this dark energy, this force that's currently expanding the universe, the components of this dark energy, and perhaps where it came from in the first place. So viewers, over the past year, cosmologists have literally been having a field day, because the first results are coming in from the new microwave background probe, the so-called MAP probe, which superseded the COBE probe originally in 1992. And it's producing some stunning results because it works at a much finer resolution. And it's given cosmologists their first true analysis of the nature of the universe. For example, its age, 13.7 billion years, 3 times the age of the Earth. It's confirmed that the universe is flat, spatially flat as predicted by inflationary theory and Einstein's equations. It's provided the rate of expansion of the universe, which is quite critical, the so-called Hubble constant, which is around about 71 kilometres per second, 0.3 million light years as you go out to the farthest reaches of space. It increases in speed by that amount. And most importantly, the distribution of mass energy in the universe, the ratio of ordinary matter to dark energy. Now, how was this achieved? Well, it was achieved because the mapping of the microwave background radiation, which emanated from the Big Bang, which emanated basically from about 380,000 years after the Big Bang, this radiation, which was stretched to the microwave spectrum, shows minor variations in temperature. And these minor variations have been picked up with much greater resolution, as I said, by the MAP probe. There's only a variation of about 25 millionths of a degree. But it's enough to show where the early galaxies formed, because the early galaxies were formed around the original fluctuations that occurred in that initial force field that drove inflation. And whether the fields are dense or not says whether produces the variations in temperature, slight variations in heat and cold. But MAP produces a lot more information than this, because it actually, within those blobs, within those early accretions of density, there are peaks and valleys also, which reflect the sloshing of early ordinary matter, baronic matter, within the early universe, backwards and forwards. And that sloshing, or acoustics wave so-called, actually reflects the distribution of the different types of matter in the universe, because they have different mechanical properties. Therefore it gives the ratio of ordinary matter to dark matter from that distribution of peaks and valleys. It shows the radiation, the variances in radiation. And this is absolutely fantastic, because again then that leaves the amount of dark energy that has to be accounted for at around 73%. Of course this wasn't understood at all back in 1929, after Einstein had developed his major work on general relativity. Hubble was the first to see that the universe was receding, was a dynamic entity. The blobs out there weren't just faint stars, they were galaxies, and they were moving away. Previously it had been thought that our Milky Way was it, the whole galaxy, the whole universe, instead of just one galaxy. And Einstein assumed that too, but he wondered why, of course, why it didn't implode from gravitation. So he stuck an extra factor into his equations called the cosmological constant to account for that, to balance that the gravitational force. But then Hubble discovered that the force was there anyway, so that constant Einstein felt probably wasn't needed, was totally unnecessary, and thought he'd made a major mistake. We'll talk a little bit more about that in a moment. But to actually now pin down the ratios of ordinary matter, and dark energy is a major, major accomplishment in cosmology. So now, viewers, we're getting to the heart of the nature of dark energy. But it becomes very murky, as you'd expect, because there are lots of theories, there are huge debates going on. There are literally hundreds or even thousands of cosmologists, astronomers, astrophysicists locked into and complex debates about the true nature of this force. So the stakes are very high at a personal level, at the institute level that they're working in, but they're very high for the whole of humanity. We have to understand this. It's not a matter of whether we'll cease to exist in 1 trillion years or in 20 billion years. The issue is understanding the universe about us. That has immense spin-offs in various ways. It perhaps produces new forms of energy, new sources of energy, new ways of understanding matter and harnessing matter and so forth. So there are relationships between these gigantic issues and day-to-day problems that confront us in the world. So the components have boiled down to about sort of 3 or 4 types. First of all, there's the vacuum energy itself, this interplay between particles and antiparticles producing energy. That's a major component, it appears, of the force driving this expansion. Whether it still exists in its original form or not, though, is not known. But there's a new player. The new player is a varying force, it's an evolving force. It's called the quintessence by cosmologists, or the 5th force, because to produce the energy that's required, and it appears to be gradually increasing, again because of this acceleration is increasing, whereas the cosmological constant or vacuum energy should be fairly constant. It's increasing because there's a 5th force at play here beyond gravity, beyond strong and weak nuclear forces and the electromagnetic force. There's an issue that's been just discovered in the form of the constants of the universe. The constants such as Newton's gravitation, the charge electron, speed of light, and Planck's constant as well, the constant that relates energy to frequency of the electromagnetic spectrum. These constants were supposed to be constant. but in fact it appears that they're changing. There is one group of these constants, again the Planck's constant, speed of light, charge of an electron, called the structure constant, or alpha, and it seems to be varying. Light seems to be in fact slowing down, and there's measurements taken to confirm this from distant quasars going back, early light sources going back 11 billion years, toward the beginning of the universe of 13.7. Light slowing down, the atomic nuclei are losing mass in the form of these funny little particles called alpha ions, and the charge of the electron increasing. This can only happen, of course, viewers, if you take into account other dimensions in the universe. It looks like our constants in our universe are sort of shadow plays that are affected by higher dimensions, because it's becoming increasingly apparent that we exist probably as a three-dimensional spatial brain or membrane, plus one dimension of time, within a larger meta-universe of 5 or 6 dimensions at least. We're floating around, and the other dimensions, as I mentioned in the previous program about relating to dark matter, have an effect on the matter in this universe and have an effect on these constants in the form, in this case, the fine structure constant. And the physics of the universe and the evolution of the universe appear to be only able to be really understood in terms of these higher dimensions, as well as in through Einstein's general relativity equations. So the constants of nature that we've taken as constants, or scientists have, are changing, are varying. This new fifth force is apparently due to the fact that as the atomic nuclei lose mass, the atoms are drawn closer together, and there's a stronger force at play there to holding them together, and that creates this extra energy. And it's a play between both the vacuum energy and dark matter, the dark matter being in the form of this alpha ion. So basically we've got quintessence on top of the vacuum energy, and again that's a dynamic energy force. There's another theory, relating to higher dimensions, quite bizarre theory called the Cartesian theory, named after the bad guys in Star Trek Deep Space Nine. Cartesian theory says that this force, this expanding, accelerating force, is caused by the tug of other dimensions on our particular 3D plus 1 membrane. It's the interplay again between other dimensions and our world. And again we've struck it with dark matter. We're striking it all over the place. Physicists are being confronted with this issue time and time again to explain empirical facts. I mean, first of all, remember that the cosmologists measure stuff like the speed of light. They're comparing the speed of light 11 billion years ago from quasars with current speed of light in a vacuum here in a laboratory in the present time. So there's definitely a slowing down, there's a change from early times, which again provides an alternate theory to the inflationary theory. There is definitely some form of evolving force beyond the vacuum energy. So that's again called the quintessence. So these aren't sort of made up scenarios. They come from ways of trying to understand facts that are being measured by powerful instruments currently. They'll only be resolved by, over time, as I've said, as the evidence accrues, it will strengthen some theories, wash out others, as has already happened with the MAP probe results. Determined the age of the universe, etc., the flatness. So over time we'll understand dark energy a lot more. But in the meantime, let's see what Einstein's equations say about it. Viewers, Einstein's equations are extraordinarily powerful. Here in the original condensed form, you have a relationship between the amount of matter and energy in the universe to the curvature it produces. This is the Riemann curvature tensor, and this is the energy momentum tensor. Tensors are mathematical geometric objects that are used to manipulate functions of space-time coordinates. But basically this describes the warping of space in terms of the amount of matter and energy in it. In other words, it's a geometric explanation of gravity. This amount of mass caused by the sun, the earth, whatever, creates this amount of curvature, and that creates gravity. Now from that equation has been derived another equation, and a large number of equations have been derived from Einstein's original equations. This is the Friedmann equation, which relates the Hubble constant, or the expansion of the universe that we described previously, at around about 71 kilometres a second for every 3.3 million light years expanding out. The expansion of the universe relating to the mass energy density in it, this term here, multiplied by Newton's gravitational constant, and this term here defines the curvature of space and the stretchiness between the distance between galaxies, the amount it's been stretched. So it relates the expansionary rate to the amount of energy, mass energy in it, and its curvature. Now conveniently from that we can just divide through by the Hubble constant squared. We get 1 equals the combination of mass density that exists in the universe. This is the mass energy density factor. This is ordinary mass and dark matter. This defines the energy density for the vacuum energy. This, the curvature of space, again, energy density function, because the curvature of space is related also to the expansionary force of the universe. And this is the energy density for the additional fields, such as the quintessence that we've described. So these are the components, or the vacuum energy and the quintessent type fields of dark energy. But basically all the components of mass energy can be combined in that one simple equation derived from Einstein's original equation, which is very convenient, and it can be represented graphically by a triangle to show the evolution from closed to open universes. So we have these 4 components again, the mass energy function, the curvature function, the vacuum energy, and the quintessence energy. And basically it shows that the universe is flat when curvature is flat, obviously. When matter dominates the universe over the expansionary forces, then the universe is closed. It goes through that transition. And when the expansionary forces, the vacuum energy, cosmological constant or quintessence, and both dominate over mass, then it's an open universe. And there's a process that you can see how the universe evolves from that simple diagram. Now, so the power of Einstein's equations allow us to very easily define how the universe evolves and its structure and everything in it. Now viewers, let's continue to examine these measurements, this treasure trove of information from the MAP probe. One of the major breakthroughs was to be able to determine the shape of the universe. Has it got positive curvature? In other words, is it a closed universe? Has it got open curvature or negative curvature? Or is it flat, zero curvature? Now this was ascertained from the shapes of those peaks and valleys again. The level of the geometry of those peaks and valleys. If the peaks were magnified, then it meant that there was positive curvature. If they were reduced, then it meant there was negative curvature. So from the geometric, if you like, distortion of those waves was able to be determined the curvature of the universe, which was obviously absolutely critical. All these key parameters are vital to understanding the whole picture and getting a grip on, again, how the universe started and how it may end. Now, of course, in recent times there's been a major startling development, and only in fairly recent times, probably going back now about a year, it's been understood that not only do we understand, the cosmologists begin to understand the shape and the components of the universe, but whether it's accelerating or decelerating. It was always assumed that mass would eventually close the universe, and it would gradually stop accelerating and reach perhaps a stable state or implode. But it's now seen from measurements of supernova that the universe is in fact accelerating. In other words, it's expanding faster and faster. Now this has been determined by sightings, measurements of the luminosity, the brightness, so-called standard candles of supernovas. They're a special type of supernova. They're a 1A type. By understanding the distance away of these different supernovas that can be ascertained by their luminescence, by their brightness, by the wavelength of that brightness, whether they are receding more, the closer ones are receding more than the ones that are further away. And in fact, now this was quite a shock, because it had been assumed that we would eventually reach some sort of equilibrium, a nice gentle downsizing, if you like. But now this major factor is thrown in, and it changes, of course, the nature of dark energy. There's a new force at play. This huge acceleration may well rip the universe apart, starting with galaxies, then worlds, then the atoms in our bodies. So in the last few minutes, before the 20 billion years are up, life would be no more. Well, viewers, let's do a quick flyover now of a couple of the theories relating to the early genesis of these huge amount of energy required to kick-start the universe. This goes back to the inflationary theories, to that enormous burst of energy that inflated the universe initially from a small seed. There are other alternative scenarios to the inflationary one, and many variations within the inflationary universe scenario. And we'll save those up probably largely for another show. But originally there was a huge burst of energy. Somehow this universe came into being. It's not mystical anymore. There's a lot of hard, solid science going into explaining it and understanding it. Again, it will take time. First of all, Einstein's equations, which we've just examined, basically say that from a black hole can emerge another universe. The equations can be solved in many ways, and one solution says that from the back of a black hole, if you like, can come another universe in a completely different set of dimensions, of course, so that we in this universe wouldn't know a thing about it. Remember, black holes swallow billions of suns, creating huge energy sources. No one knows exactly what happens to that energy as it disappears into the black hole, as it's swallowed up. But it is possible, through mathematics, again, to understand that a new universe could emerge. So perhaps we're all born in a black hole and out of a black hole. There's some very interesting geometries that go on in a black hole as well that sort of simulates a sort of Doctor Who's TARDIS. We could go into a microscopic black hole, disappear, all of us, but when we got in there, it might appear as a vast universe again. We could have emerged into this. Of course, the end of the universe has been debated for a long time, at least a century. When laws of thermodynamics and entropy were understood, it was called then the heat death. In other words, it was understood that over time hotter objects would gradually get cooler, and that would go for hotter objects in the universe as well. And over time it would become just random noise, random states in the universe, and life would cease to exist. A lot's been learned since then, but that's one absolutely plausible scenario, because there's no doubt. But either way, if things look very grim for life, perhaps they'll choose an escape route. They've got several. One, they could manufacture a black hole and escape perhaps into another universe. The other option is to escape perhaps into higher dimensions, which are still, of course, at this point in time, untapped. And then again, perhaps there's Other scenarios where they've simulated life, perhaps us, and transplanted us to another universe. I'm David Tao, and you've been watching the Theories of Everything program. I'll look forward to seeing you again next week. We in this universe wouldn't know a thing about it. Remember, black holes swallow billions of suns, creating huge energy sources. No one knows exactly what happens to that energy as it disappears into the black hole, as it's swallowed up. But it is possible, through mathematics, again, to understand that a new universe could emerge. So perhaps we're all born in a black hole and out of a black hole. There's some very interesting geometries that go on in a black hole as well that sort of simulates a sort of Doctor Who's TARDIS. We could go into a microscopic black hole, disappear, all of us, but when we got in there it might appear as a vast universe again. We could have emerged into this other universe. Viewers, if life's